The slides contained within this presentation were created by the math educators that participated in the video project and recorded through the Indiana Department of Education. They provide a detailed look at the standards for mathematical practice that can be utilized to create a deeper understanding of the practices. With the implementation of Common Core, many educators are leaving out the implementation of the standards for mathematical practice, or SMPs. The content standards are important, but the practices are an equal asset to an effective math classroom. This project hopes to help teachers develop a better understanding of the mathematical practices and how they can be integrated into their daily lessons. What we want teachers to understand is that the practices don't guide your lesson, your content guides your lessons. But the practices need to be a natural part of the process. It's not something that you do on Fridays or a special day. It happens each and every day in every math lesson. These are the 8 standards for mathematical practice as outlined by the Common Core. Unlike the content standards, which identify a specific grade level, these standards should be integrated into content instruction at all grades K through 12. The Common Core define these as processes and proficiencies with long-standing importance in math education. This is what we want students to take away believing about what mathematics is as a field. Too often, students develop beliefs and dispositions about mathematics that suggest it's not applicable to the real world, or that mathematics is mostly about learning rules without understanding. The practices emphasize the importance of highlighting math as a field that is focused on problem solving, understanding, justifying, and representing quantitative thinking. We want students to leave their K-12 mathematics experiences with a realistic view about mathematics as a field that focuses on inquiry and knowing that they can apply their thinking. One of the things to make clear is that these practices are not content specific. Unlike many content standards, you probably will not be able to spend a few days on constructing viable arguments and expect students to have mastered this practice. Rather, these practices should be inherent in your daily instruction and sustained throughout the year. Every lesson should ideally address one or more of these standards, and you should revisit the standards regularly. The Indiana Department of Education and others have suggested that the mathematical practices be paired to emphasize important connections between them. Problem solving and precision are overarching ideas, and the others can be grouped to focus on reasoning and explaining, modeling and using tools, and seeing structure and generalizing. We will be discussing each of these 8 standards in greater depth throughout this webinar. Mathematical practice number 1 is making sense of problems and persevering in solving them. Before we look at this practice more closely, it's important to understand what a problem truly is. According to this definition, a problem is defined as any task or activity for which students have no prescribed or memorized rules or methods, nor is there a perception by students that there is a specific correct solution method. This may not be how you've thought about problems, but it's important when thinking about this first mathematical practice that you focus on this or a similar definition. As teachers, we often want to help students solve problems by providing too much assistance. Keep in mind that if we remove all obstacles to problem solving for our students, we're not supporting the perseverance aspect of this practice, and we thus deny students the opportunity to make sense of math. What should students be doing while engaged in this practice? They should explain the meaning of the problem and describe possible approaches to a solution. They should ask themselves, is this similar to one I've solved before? If so, what approach did I use then that may work now? They should use resources such as manipulatives or other concrete objects and drawings to help them think about the problem. They should monitor and evaluate their progress. Do they recognize when the method they are using isn't working? They should change strategies if needed. And finally, they should check their answers using a different method. If the students check their answer using the same approach they used to solve the problem, the student may conclude that their solution is correct when it's not. But if they check their answer using a different method, they are apt to find the errors in their reasoning and eventually come to the correct solution. All of these ideas help students to not only make sense of problems, but to persevere in solving them. Choosing a good task or problem is critical to engaging students in this mathematical practice. Here's an example of a problem that might be given to 5th graders. This problem was chosen because the context would be interesting to many students and it would challenge them. It builds on the work that they've done in 4th grade, where they divided by 1-digit numbers, and it supports the use of multiple strategies. Students might use repeated subtraction, they might rely on their knowledge of multiplication facts, or they might use some type of manipulative like base 10 blocks. Here is a problem for kindergarten. We chose this example because the problem addresses meaningful math. What do I mean by meaningful mathematics? I'm referring to mathematics that will propel or move students forward in their mathematical knowledge at an appropriate level. And through the use of manipulatives and written work, the problem will reveal information about their understanding of how to decompose numbers. To decompose a number means to break it down into 2 or more parts. In this case, they are decomposing the number 5 into 2 parts. To help students meet this standard, teachers need to provide good problems. This is one of the most important decisions that you will make for your students. You may be thinking, how do I know if it's a good problem or not? Here are some questions that you can ask yourself to help make that determination. Let me add some clarification to the last question. What we mean by students' interactions with the problem are such things as students' work, their discussions, and the processes and strategies they use to solve the problem. You want to be able to look at student work and listen to their discussions and gain information about their understanding of mathematics in the task. There are 2 examples referenced, one for 5th grade and one for kindergarten. But keep in mind that you are the best person to answer these questions for tasks that you choose because you know your students better than anyone. In addition to choosing a good problem, you should facilitate engagement in the problem-solving process. You can do this by having a variety of tools and resources available for them to use by encouraging questions. One question from a student can lead to very interesting class discussion. And finally, you want to support students as they try to make sense of the problem. Help them make connections to similar problems they've solved and ensure the students always check the reasonableness of their solutions. We all know of instances where students come up with a solution that makes no sense in the context of the original problem. One way to help students is by having them estimate the solution before they even start solving. The math practice of attending to precision relies heavily on the mathematical norms established in the classroom. Developing this mathematical practice is dependent upon students' realization of appropriate use of informal and formal mathematical language, procedures, and processes that they engage with mathematical problems. This mathematical practice is comprised of 4 sub-skills: communicating precisely to others, stating the meaning of symbols and definitions and using them appropriately, specifying units of measure, and calculating accurately and efficiently. Attending to precision focuses on the need for both teachers and students to communicate precisely and correctly. Precise mathematical communication could involve understanding and appropriately using symbols, definitions, and units of measure. This practice requires the students to be accurate and appropriate in the use of calculations, keeping in mind that the level of appropriateness is often determined by the context of the problem. Students in a 3rd grade class were asked to respond to the question shown here. The question is discussed in more detail as an example of mathematical practice number 3. The class discussion leads to an insightful exchange about the importance of recognizing the whole in context when comparing what seems to be equivalent fractions. As part of the discussion, the teacher models the mathematical practice of attending to precision by introducing terms and their respective definitions for the numerator and denominator, as well as recognizing the importance of the context when determining the appropriate quantities to compare. Students in a 6th grade class were asked to respond to the question shown here. The question is discussed in more detail as an example of mathematical practice number 3. Through orchestrating a classroom discussion that highlights these 2 solutions, the teacher models the math practice of attending to precision as she asks each student to explain and support his or her solution strategy. This discussion leads to an insightful exchange that produces 3 equivalent equations to represent the pattern. The teacher takes the opportunity to record the equivalent equations and discusses the meaning and uses of the algebraic symbols involved in each. The teacher's role in helping students develop the math practice of attending to precision includes modeling the appropriate use of mathematics vocabulary, symbols, and explanations, providing opportunities for students to share their thinking, and preparing students for further study. First, teachers help students attend to the importance of precision by modeling appropriate precision when discussing solutions to problems. This modeling often comes into play as student strategies are being recorded for the class. Oftentimes, as strategies are shared by students, informal language is used to describe their process. It is important for teachers to stress the importance of the use of mathematically correct vocabulary and symbolism as these strategies are recorded. Providing opportunities for students to share their thinking engages the entire class in determining mathematical precision. Other students, as well as the teacher, in developing proper language to describe mathematical precision. Finally, teachers should think ahead by using appropriate language that supports the further study of mathematics. Statements such as multiplication makes bigger and division makes smaller hold true for whole numbers, but often lead to misconceptions in the further study of integers, fractions, and decimals. The mathematical practice of reasoning abstractly and quantitatively relates to students' sense-making skills. The students make sense of mathematical situations by carefully thinking through ideas, by taking into account examples, counter-examples, and other alternatives, and by forming and reflecting upon questions, conjectures, and hypotheses. The ability to reason abstractly and quantitatively forms the foundation for student engagement in all areas and levels of mathematics. This mathematical practice is comprised of 3 sub-skills: making sense of quantities and their relationships in problem situations, contextualize and decontextualizing mathematical situations, and creating a coherent representation of the problem at hand. Reasoning about quantities and their meanings is of particular importance in the learning of mathematics. Understanding and sense-making around quantities include the abstract understanding of quantities expressed through symbols, as well as the understanding of quantities expressed in context. This mathematical practice is firmly based in number sense and stresses the importance of the development of students' sense-making skills in both concrete and abstract representation of quantities. These examples from first grade illustrate the basic ideas of contextualizing and decontextualizing simple mathematical solutions. In the first, students are asked to reason abstractly about an additive mathematical situation by decontextualizing a mathematical story. In the second example, students are required to ponder the underlying meaning of the operation of subtraction. Oftentimes, students are encouraged to look for keywords and problems that are associated with mathematical operations. These examples illustrate the consequences of relying solely upon the keyword approach to problem solving. Mathematics education researchers use the birthday problem shown here in their research on children's mathematical problem solving. In the study, 10% of the participating kindergartners and first graders attempted to answer the question posed by either adding or subtracting the 2 numbers involved, even though sufficient information is not presented. The percentage rose to 30% for the second grade participants. The results show that even 45% of fifth graders attempt to solve the problem. The study results highlight the importance of developing the ability to reason through mathematical situations, including the ability to make sense of the situation while decontextualizing it. This example illustrates the importance of students making sense of the context. The keyword more is associated with the act of summing and generally indicates an unknown result. However, in this problem, the initial value is unknown rather than the result. Students relying on the keyword approach to problem solving run the risk of choosing to find the sum of 6 and 14 rather than the difference. This 6th grade example is from the National Assessment of Educational Progress, NAEP, and requires students to reason about the division of fractions, a concept that is difficult for many children and adults. Here, students are asked to contextualize a mathematical situation involving fractional parts of a whole consisting of 3 objects. Creating a context such as how many people will receive servings of half of a pineapple if the restaurant has a total of 3 pineapples around this mathematical situation provides students the opportunity to reason deeply and conceptually about division involving fractions. The teacher's role in helping students develop mathematical practice of reasoning abstractly and quantitatively includes providing opportunities for students to strategically reason about number quantities and their applications. First, teachers provide distinct opportunities for students to develop number sense to form a foundation for mathematical reasoning. Providing students the opportunities for developing a deep number sense includes empowering students to express interpretations about numbers by relating quantities in abstract ways with the application of quantities in context. For example, the numbers 5, 17, and 32 can be related to each other by comparing which sets are greater or less than the others, or considered in context as fifth place, 17 ounces, or age 32. Providing students with the opportunity to apply relationships between numbers supports student number sense by promoting mathematical efficiency. For example, knowing the relationship between numbers 3 and 9 allows students to replace 1/3 with 3/9 in the problem, 1/3 plus 4/9, to efficiently solve. Students also need opportunities to recognize the magnitude of numbers in context in order to make sense of their world. For example, children may consider $93 to be a large sum of money, but 93 grains of rice would be very small serving of food. Providing students with the opportunity to use multiple computational strategies as well as multiple representation of numbers facilitates a development of deep number sense. Generalizing about computation based on individual cases is important. For example, realizing that a number multiplied by 2 is the same as doubling the number or multiplication does not always make the product bigger are big conceptual ideas. Providing students opportunities to make decisions involving numbers in their own lives is paramount to the development of strong number sense. Opportunities to translate information into algebraic representations of contextual problems to use in the problem-solving process results in increased number sense. In the classroom, it's important for teachers to draw students' attention to numbers and their applications by considering numbers to be a source of exploration for students. Teachers should encourage classroom discourse that promotes going beyond the answer. Through the teacher's use of probing questions, students' thinking can be stretched beyond the answer to the underlying mathematical connections between quantities being considered. The mathematical practice of constructing viable arguments and critiquing the reasoning of others relates to students' analysis of various mathematical situations. Students make conjectures and arguments in support of mathematical situations while listening to and judging the reasonableness of the mathematical claims made by others. The ability to construct viable arguments and critique the reasoning of others forms the foundation for student mathematical communication. The mathematical practice is comprised of 5 sub-skills: understanding and using stated assumptions, definition and previous results, analyzing situations, justifying conclusions, comparing 2 plausible arguments, and determining the domains to which an argument applies. Constructing viable arguments and critiquing the reasoning of others focuses on the process of solving problems and provides students with the opportunity to describe how they solve problems and how their problem-solving strategies connect with the strategies of others. Students in a 3rd grade class were asked to respond to this question shown here. Student A drew an illustration showing how Jose could be right, while student B supported Ella's conclusion. Alone, these responses are appropriate, but do little to build the understanding of the importance of the congruent wholes when comparing fractions. Through orchestrating a classroom discussion that highlights these 2 solutions, the teacher can ask each student to explain and support their position and engage other students in the class by asking them to restate each position in their own words. This leads to an insightful discussion about the importance of recognizing the whole in context when comparing what seems to be equivalent fractions. The teacher then extends a problem by asking students if they can create an example in which Ella would have eaten more pizza than Jose. Students in a 6th grade class were asked to respond to the question shown here. After students answer the initial questions, the teacher realizes that students are having difficult times generalizing an equation that describes the pattern in determining the number of toothpicks in n hexagons. Student A is close to forming a generalization, but the student does not recognize the generalization. Asking student A and student B to share their work to find the number of toothpicks in 5 hexagons with the class orchestrates a classroom discussion that highlights these 2 solutions. You can engage other students in the class by asking them to restate each position in their own words. This discussion leads to an insightful exchange that produces 3 equivalent equations to represent the pattern. The teacher's role in helping students develop the mathematical practice of constructing viable arguments and critiquing the reasoning of others includes establishing supportive social norms in the classroom, providing opportunities for students to make and evaluate conjectures, and facilitating meaningful discussions of mathematics. First, teachers can work towards establishing supportive social norms in the classroom by modeling appropriate behaviors when discussing solutions to problems. By sharing several correct solutions to the same problem, teachers can emphasize the importance of reasoning behind each solution, resulting in a focus on the process. Teachers can provide opportunities for students to make and evaluate conjectures by asking students to consider alternative solution paths for problems, as well as extending problems to other cases, as in the pizza problem shared earlier. Teachers facilitate meaningful discussion of mathematics by either providing opportunities for students to discuss and question each other's mathematical thinking, or by asking probing questions to help mathematical thinking emerge when student discussion is stalled. This practice is often misrepresented, mainly because of the word model. Some believe this word either means to show something or represent it using a physical model, but that's not the sole intent of the practice. The most important aspect of this mathematical practice is application. Can students apply mathematics to real-world contexts? When they are solving these real-world problems, are they attending to what assumptions they are making and the impact of these assumptions on their solution? Do students have opportunities to identify the quantities they need and use tools to represent their thinking? Finally, do students think about whether their answer is reasonable? The knot that ties all these ideas together is the importance of solving authentic, real-world problems that require mathematics. For example, the real-world scenario and symbolic models shown here are common in first grade. Students' first encounter with models usually involve the solving of early word problems. Their mathematical models may be in the form of an equation like the ones given. Students should attend to the operations and order of numbers in their models. As students progress through the grades, the ways they model and represent situations will change as students learn more mathematics. For example, whole number division is an important content focus in grades 4 and 5. Consider the division problem 25 divided by 4. What's the answer? Well, depending on the context of a real-world problem, we make assumptions about how to report the answer, with a remainder, as a decimal, as a fraction, or by rounding. Some textbooks ask students to use one of the methods without helping students to think about why. Students should be given opportunities to reflect on what a reasonable answer is for a given context. Part of modeling is understanding what assumptions are being made when solving a problem and what answers are reasonable. In grade 8, students begin to analyze data involving two variables. Data modeling might include creating scatter plot and lines to fit the data. This question may easily be extended to have students make estimates using the line of best fit. For example, you might have students estimate the score on the test for a student that missed 2 class sessions. This problem requires students to produce multiple representations. However, it also engages students in a problem in a familiar context. One way we model mathematics is by representing math in multiple ways. In early grades, students experiment with represented problem situations in multiple ways, including numbers, words, drawing pictures, using objects, acting it out, making a chart or list, creating equations, and so on. Students need opportunities to connect the different representations and explain the connections. They should be able to use all of these representations as needed. To help students meet this standard, teachers need to provide opportunities to solve real-world problems. The more authentic these problems are, the better. Even with your own school or community, there are many ways you can connect the mathematical work of your students. Focus on sense-making and reasonableness of the results. Although students can often develop ingenious ways of solving problems, you want students to be able to consider whether their solutions are reasonable and appropriate given the constraints of the context. Finally, we often have students solve word problems. One of the ways to strengthen students' ability to model is by having them develop the context or word problem. For example, you might have students write a word problem for 4/5 minus 1/2. Students must be careful that they are attending to the whole when writing such problems. The nature of mathematics facilitates the use of the variety of tools for teaching and learning. In fact, some math content like measurement requires the students to use appropriate tools. Take a look at this picture. Not using the right tool can often create an increase on the burden of doing mathematics, which in turn can cause students to develop negative impressions of mathematics. So what do we mean by tools? Of course, tools in mathematics could include the traditional tools we've used in math classes like a protractor to measure angles or compass to construct arcs. But it also means technological tools like calculators and computer software for geometry or data analysis. Manipulatives can be considered tools such as pattern blocks or base 10 blocks. Finally, the word tool can be extended to include conceptual tools such as different types of graphs or common formulas and algorithms that are used to accomplish a task. Even estimation is considered an important mathematical tool needed to solve problems. Thus, tools can represent a wide variety of mathematical devices, both physical and conceptual. Knowing how to use mathematical tools is only part of this practice. In addition, students need to know when a tool is appropriate to use and how to use them strategically in their work. In kindergarten, students learn to decompose numbers. Students should use many tools such as two-color counters, 10 frames, unifix cubes, and part-whole representations to represent these decompositions. Students should be familiar with these different tools and understand how they can use them to help them construct their arguments about different ways numbers can be decomposed. In this problem, students were asked to determine how many unique pairs of main dishes and drinks can be made. To solve the task, students may use a variety of conceptual tools like a tree diagram, a table, or the multiplication counting principle. Students should be aware of the different choice of tools that they have in solving such problems. Some teachers like to always select the types of tools that students use, but it's important that students develop the ability to choose appropriate tools to express their thinking. Students in 7th grade are expected to be able to construct geometric figures with given constraints or to provide reasoning if a figure cannot be constructed. Technological tools like Geometer's Sketchpad can be useful to aid students in creating constructions and arguments. For example, this figure was used to justify why the triangle inequality theorem holds true, showing that you cannot create a triangle with the side lengths of 6 centimeters, 3 centimeters, and 2 centimeters. In evaluating the instructional value of a technological tool, it's important to focus on whether the tool provides a means to further the student's mathematical thinking by giving new insights. To ensure this practice is met, teachers need to provide students with access to appropriate tools, facilitate that selection of tools. Remember that many tools have multiple purposes and can address different content areas. For example, two-color counters are useful for teaching topics in whole number operations, fractions, and probability, and help students become aware of the power of tools. Remember that tools should not only be used to simply for the sake of using tools, but rather the tools should support the student's ability to engage and develop mathematically. Mathematical practice 7, look for and make use of structure. Students are familiar with structure in their daily lives. The routines that they follow on a daily or weekly basis provide structure for their time. There's also structure in mathematics that students should look for and make use of. And just as with structure in our lives, structure in mathematics helps us know what to expect. In fact, a major contribution to the beauty of mathematics is its structure. Students should explain the patterns and structure they see in mathematics. They should shift perspective and view things as a single object or as composed of several objects. And finally, students should explain why and when the properties of operations are true. Do they know, for example, when the commutative property holds? Do they know why it works for multiplication? Students in 3rd grade are expected to apply properties of operations and mental math strategies to multiply and divide. Here are 2 different ways that students might multiply 7 times 8. The student on the left used an array to help visualize the problem and to decompose 7 into 5 plus 2. By using the structure of the array, the student used the 2 easier multiplication facts to find the product of 7 and 8. The student on the right used a related number fact, 7 times 7, to help him find the product. He decomposed the number 8 into 7 plus 1. Both students looked for and made use of structure to solve the multiplication problem. Students in 5th grade are asked to examine the pattern in the number of zeros that appear in the product when multiplying a whole number by powers of 10. Often students learn a rule for multiplying by 10, 100, and so on. If you multiply by 10, add 1 zero. If you multiply it by 100, add 2 zeros. But they don't really understand why the rule works. This figure illustrates that when one multiplies by 10, the value of each digit in the original number becomes 10 times larger. Here you see 10 groups of 34 toothpicks. Looking top to bottom, you can see that each group of 10 toothpicks in the 34 becomes 10 tens, or 100 toothpicks. Each single toothpick in the 34 becomes a group of 10 toothpicks. Looking across the bottom of the slide, one can see that after multiplying 10 times 34, we now have 3 hundreds and 4 tens, or 340. The result is that each digit shifted one place to the left. That is why we add a 0 on the end of 34. The structure of our place value system helps us explain why this rule works. Another domain in the Common Core standards is geometry. The study of geometry relies a lot on the structure of objects. Here are two area problems. In the first example, students are asked to find the area of a trapezoid, using only formulas for rectangles and triangles. In order to complete this task, students need to shift perspective and see the trapezoid as composed of smaller shapes. In the second example, students must use the structure of the circle to decompose it into wedges that can be rearranged into the shape of a parallelogram. Then, using prior knowledge of how to find the area of a parallelogram, they can derive the formula for the area of a circle. To help students meet this standard, teachers need to draw students' attention to the structure in mathematics. To do this, you need to provide an appropriate examples that will encourage students to notice the structure and allow them time to talk about and share their findings. There are a lot of patterns and numbers, and these patterns can be represented in different ways. They provide one context for recognizing structure in mathematics. And finally, help students make use of structure. Noticing structure is only the start. Being able to apply that structure to new situations will help students solve problems efficiently and effectively. Practice number 8 really urges the educator to let go so that students can find the repeated reasoning. When engaged in this practice, students move beyond simply solving problems to finding ways to generalize the methods that they use and to determine shortcuts for those procedures. Students should notice if calculations are repeated and use that information to solve problems. They should use and justify the use of general methods or shortcuts. The word "and" is important here. Often students can use a method or a shortcut but don't understand why it works. And finally, do students use metacognitive skills? In other words, do they think about their thinking? In particular, do they ask themselves if a strategy makes sense as they work? Do they check for reasonableness? These are all important skills that will help students notice the regularity in their reasoning. In mathematics, regularity in reasoning means the ways in which students generalize methods or justify shortcuts. Let's look at some examples. In third grade, students investigate whether order matters when multiplying two numbers. In this example shown, we can see that it is not immediately obvious that 3 groups of 6 is the same as 6 groups of 3. Initially, students may need to count to verify this. After a few similar examples, students conjecture that the order doesn't matter when multiplying. The commutative property for multiplication can be further illustrated through the use of arrays in which the number of rows and the number of columns are interchanged. In 5th grade, students divide whole numbers by unit fractions. Here's an example. Angelo has 4 pounds of peanuts. He wants to give each of his friends 1/5 of a pound. How many friends can receive 1/5 of a pound of peanuts? A diagram like the one shown can help students to solve the problem. Students may explain the solution like this. Since there are 5/5 in one whole, 5 friends can share 1 pound. There are 4 pounds, so 20 friends can each receive 1/5 of a pound of peanuts. After more problems like this one, students conjecture that the solution can be found by multiplying the number of wholes by the number of parts in each whole. This thinking eventually leads to the shortcut we all know and use: invert and multiply. In 8th grade, students study transformations such as reflections and rotations. After completing several problems, students may notice that when an object is reflected across the y-axis, the x-coordinate of the image is opposite of the x-coordinate of the pre-image, and the y-coordinate stays the same. In a similar manner, when a figure is rotated 180 degrees about the origin, students notice that each coordinate of the image is the opposite of its pre-image. When students look for and recognize this regularity, transformations become easier to perform. To help students meet this standard, teachers need to avoid teaching shortcuts before students develop the understanding of important concepts. When students can make sense of a process or method, they take ownership of it, understand why it works, and are less likely to use it incorrectly or inappropriately. The only way this will happen is if the conceptual understanding comes first. Teachers should scaffold the examples they use so that the students move from seeing the repeated reasoning of a single example to being able to build a general method. Asking students to describe the processes that they use and look for repetition in those processes provide the scaffolding needed for students to make sense of the method. And finally, it's important to establish classroom norms for student expectations. Students should be expected to make and share conjectures related to what they notice. Our primary reference for this webinar has been the book series Common Core Mathematics in a PLC at Work, co-published by Solution Tree and the National Council of Teachers of Mathematics. For any further questions, please don't hesitate to contact me at the information provided here. Thank you.